Okay, so since we waited a little bit, I guess we can get started. So welcome everybody. Again, sorry, apologize for the issue. I assume I still see some few people trickling in, but it's a pleasure to have Dan Crisan, give us a seminar today. So one of the reasons we invited Dan was because he had a large projects on mathematics of planet Earth at Imperial for 5 years, and has a long history in MPE. And so he's professor at Imperial College, and he has received many awards and works on uncertainty quantification and transports and ocean application. So, and reduced order modeling. And was that I won't make the introduction too long, and so it's a pleasure to have you here, Dan. And you can ask questions at any time, and we look forward to your presentation.
Thank you very much, Pierre, and thank you for the invitation to give a talk at this activity group in the mathematics of planet Earth. And for me, it's a new audience. But really, I have been involved in the mathematics of planet Earth ever since its inception in 2013, which perhaps some of you know, most of you might not know. This was the year of the mathematics of planet Earth. And many of us were excited that this is going to be something that we should all work into. And over the year, the work in the mathematics of planet Earth has continued. But I somehow feel that perhaps in the recent years, because of external pressures, we had COVID, we have wars and so on, somehow the focus on the mathematics of planet Earth has diminished. And I thought I will devote the first 10 minutes of my talk to talk a little bit about the mathematics of planet Earth challenges of the 21st century. The material that I will present is based on an initiative that is called the Mathematics of Planet Earth and Future Earth initiatives. Some of it was on a website at Rutgers, but I was very surprised to see that the website has gone down. And if people in the audience know people from Rutgers, perhaps they can get in touch and perhaps they can resurrect this website. So I'll say a little bit about the challenges of our mathematics in the current context, and then I'll move on and start presenting my talk. I will talk about uncertainty quantification for geophysical fluid dynamics models and how you add stochasticity in geophysical dynamics models. And this comes under the name of stochastic parametrizations. But once you assume that you're going to add stochasticity, then you have to calibrate these stochastic terms. The stochasticity comes as an effect on the deterministic equations, the PDEs that govern the geophysical fluid dynamic models. And therefore, you end up not with a PD, but an SPDs. And so the bulk of the talk will be looking at how you calibrate SPD. So this is kind of the more theoretical part of it. And then I'll spend as much time as I can on case studies that we've had related to the stochastic rotating shallow water model. I'll conclude with some final remarks, and then right at the end, I will advertise our own program which is devoted to stochastic transport in the upper ocean dynamics, and invite people, if they are interested, to come and join us, get in contact. We have lots of activities, but I'll come to this hopefully at the end. We have a paper that I forgot to change this, has just appeared like 2 weeks ago, but you can get the paper from the archive. There's no difference. So if people are interested to learn more about the subject matter of this talk, they can look at this paper. I take it, Pierre, that I should also stop at 5 o'clock, right? So I have about 45 minutes left. Am I right?
Yeah, more or less. Yeah.
Okay, so I'll try and stop on time, but I don't want to start talking about the maths without talking a little bit about our challenges for the mathematics of planet Earth. And the way in which these challenges were structured back in 2013 and after that, there were 4 global challenges, 4 major challenges. The first one was understanding the physical Earth. And there's 4 subheadings here: oceans, atmospheres, biosphere, and cryosphere. I have been working in the first one with some, but also in the second one, and also looking at the interface between ocean and atmosphere. So each of these has lots of things that people can look into and contribute to. So this is the first challenge. The second challenge is understanding Earth as a system supporting life. So not just as a physical system, but as a system supporting life. And there's again 4 substrands for this one. One is ecology, carbon cycle, which is kind of very important, and we are all suffering because of the disruptions in carbon cycle, food systems, and sustainability as a result of the current problems with climate change. This is the second global challenge for mathematics of planet Earth. The third one is looking at human activity in itself on our planet. And here again, we have 4 subheadings: land use, energy, transportation, and epidemics. And it was the epidemics that played a major role in the last few years with the COVID-19 pandemic and so on. But they are continuing, and there's a lot of work that can be done and should be done in this area. Finally, we have the global challenge of Earth as a system at risks. And then in here, obviously, we have climate change. And I don't want to talk to you about the problems and the mathematical problems that are related to climate change. But we are all affected by this, and somehow it feels to me that the people that govern the planet, the politicians, are still not yet there to understand how critical climate change is. And we only have to look at the recent COP meeting and see how little progress has been made when climate change poses such critical challenges to humanity as a whole. This is not the right place to make more comments on this, but it does feel to me that we don't make enough progress in this area, and we are scientists, we are mathematicians, should get involved more than we do. Next comes biodiversity, water, food security, and then obviously extreme events. All of these are important, and all of these are systems, individual systems that are currently at risk. Okay, so I'm going to stop here. I wish I had a bit more time to tell you about this, but these are all topics, these are all directions of research where mathematicians can come and can make an impact as part of the mathematics of planet Earth area. Okay, so let me move on to my talk, and I'd like to preface the talk by saying a little bit about stochastic parametrization, and in general, why is it important that you have stochastic parametrization? And maybe this is already well understood by the audience. I don't know what the audience background is, but let me just say that in all models related to numerical weather prediction and climate prediction, the way this is done is by using continuous equations of motions which are then discretized both in time and in space. And the resulting discretization is then implemented. You use numerical programs which are jointly termed dynamical core, and they are used to model weather, to model all the parameters, all the variables that will decide the weather or climate. And these are on the resolved scales. So, if you have a discretization grid, of course, all these models are solved on the grid itself, and anything that is subgrid is not solved, is not there. So you only get estimates for the grid scale effects of such models, of such processes. Whatever is below that is not there. Nevertheless, even with these estimates, current predictions are quite good, quite skillful, and we live in a period where there is reasonably success in both forecasts for weather and perhaps less success in climate prediction. But it has become apparent that there's lots of problems with the current state of the art of the models, and there are persistent and systematic shortcomings because of the fact that the unresolved processes are not adequately represented through deterministic parametrizations. Now, of course, there exists a continuous drive to increase computing power to have higher and higher resolutions for these ones. But the understanding is that there's a lot of important physical processes, including, for example, tropical convection, gravity wave drag, microphysical processes, and so on, that will not be resolved at the current or in the next 20 to 30 years development of computational power. Of course, the parameterization of subgrid processes will raise other problems, closure assumptions, parameter estimations, and all of this will bring uncertainties. And there is a hope that by using stochastic parametrizations for estimating this uncertainty coming from subgrid scales in weather and climate will help to reduce these model errors and will help to capture responses to changes in external forcing. And I have here a quote which is taken from a paper which perhaps some of you have seen it from, which was published in 2017 by the American Meteorological Society, called Stochastic Parameterization Towards a New View of Weather and Climate Models, and it has been signed by a large number of people that work in this area. So this is not your run-of-the-mill paper. It's a paper where it's sort of a blueprint for what's to come. And so, the key finding for this paper is the following: stochastic parametrizations empirically derived or based on rigorous mathematical and statistical concepts have great potential to increase the predictive capability of next generation weather and climate models. So this is the finding of this paper. And what I will do today is to go in this direction to explain that once you have a stochastic parametrization, once you agree that you will use a stochastic parametrization, I will explain how you calibrate the stochasticity in your parametrization. And I'm going to start very simply and try to be as general as possible, because the method that I will present is indeed generic. And I will explain what I mean by that. So let's suppose that you have a geophysical fluid dynamic model. I should be model there, that is satisfies this PD. So I'm writing it in very abstract terms, right? So is the solution of this PD. I'm going to call this the solution by M with a superscript F, and F is going to be coming from phi, because it's going to be a high resolution model, okay? And what you do, you say, okay, this high resolution model may be a model that you run on your high resolution, high parallel computing facility. And what you want to do, you want to work with a low resolution model instead of it. Or it may be that you think of this high resolution model as the real thing, and you want to work with a discretized version of this, a lower resolution model than the real thing. And so what you do in order to account for the missing scale, for the effect of the unresolved scale, is to add a stochastic term in here. And so the way to look at this stochastic term is to say, okay, there's an operator here that will give you the deterministic part, the actual PDE, and there's another operator here that appears in front of the stochastic term in here. So this stochastic term will drive the whole stochastic PDE this time. So your choice, your decision should be that you say, well, okay, so I'm going to model the amplitude of the stochasticity by another operator, M, which will depend on your solution. And the solution now has lost the F in here and has received the C in here, because this is going to be the solutions that models tries to approximate the high resolution model, but on the low resolution scale. So this is going to be your choice. And then you have to have this random process in here. So the question is, what is this random process? So this random process is written in here, is effectively just a sum of Brownian motions, okay, multiplied by some vector fields. So these psi k's are vector fields, are not just constant, but are vector fields which are space dependent. Okay, so the way in which you introduce the you model the subgrid scales is by adding this term. It is your choice to decide how you're gonna introduce this operator, and then you have to have this stochasticity added to it. And the question in here, what kind of stochasticity add to it? In particular, how do you calibrate this psi k? So everything else in your equation is going to be given, either coming from the final resolution model or your decision how to model the subgrid scales, in other words, this M. But the purpose of this talk is to explain how do you model this, how do you estimate this psi k's based on data. Okay, so the reason why I say this is generic is because what I'm going to show you next is independent of the A, is independent of the M, and it can be applied to either real data or to simulated data. So a simple example here, very theoretical, but it's very simple so that we understand. So suppose we're looking at the 2D Euler equation. You're looking at the vorticity form of the 2D Euler. So that's the vorticity of the fluid. That's the form of the 2D Euler equation, and you can definitely write this down. This is the operator which is written in this form. And then you say, okay, now I don't want to work with the deterministic equation. I'm going to work with a stochastic PDE. I'm going to perturb the 2D Euler and end up with an SPDE that has the deterministic part common with the 2D Euler. So what sort of parameterization you could include? Well, what you could include in here, you could just add the noise as is. So this is called an additive noise. Or you can include multiplicative noise. Multiplicative noise means that you take the solution, the vorticity itself, and integrate it with respect to your cylindrical Brownian motion. Or it can be transport noise. In other words, you have the grad perp of omega integrated with respect to your cylindrical Brownian motion, and so on. And in each one of these, you can see what the M is. Okay, so the question is, for each of these equations, the question would be, suppose I have data that is coming, say, from the 2D Euler equation in vorticity form, deterministic. How do I compute now disk size that appear in the stochastic term? And this circle here simply means Ratonovich integration. I'm not going to explain to that. And in the example that I'm going to show, one of the examples that I'm going to show, if there is time, you'll see that I can have a high resolution model that is on a square 512 by 512, and then you coarsen it. You go to 64 times 64. You solve the SPD on the lower resolution model, and you want to compute. You want to estimate this psi. Okay, so that's the plan to do this, and okay, so now I need to go to the next page. Hopefully it's gonna work. Okay, so I'm gonna give you just the strategy, the general principle of doing this. So the data is gonna be the solution of the PDE. So you have to have the solution of the PDE, or this can be real data that comes from satellite observation or any other type of observation. So what you do, you take the difference between your fine resolution model and a modification or a low pass filter of the data, right? So you want to look at what happens, what is the difference between the actual solution and the coarsening, if you want, of the data, a modification of the data. So this difference is meant to kind of measure the loss when you're coarsening, the subgrid scales influences. So you look at this difference and you denote this difference by m hat. And what you do next, you take increments of this process. You take small increments of this process. And when you take small increments of this process, you'll say, okay, these small increments of this process, which should come from the subgrid scale effects, should look like, the ansatz is that they are an integral of your operator M applied to this modification of the fine dynamics integrated with your cylindrical Brownian motion. And when you discretize this thing, you end up with this expression. That means you assume there's going to be a finite number of Brownian motions, and this n you have to find what this n is. Then you have this thing which is observable, and then the psi-k will have to be computed. So what you want to do, you want to start with a partition of the time interval. You have to compute these increments, right? And then you compute the psi-k by using a principal component analysis procedure. So that's the basic idea. And you see how this is applied in practice. It's not really quite straightforward to get to the principal component analysis. There is an intermediate step in between, but basically this is the plan, and it can be applied to really any type of PDE and any type of parametrization. And the remarks that I'd like to add in here are as follows: that theoretically, right, because I'm come from the theory, you define them on the same physical domain, but when you numerically approximate these things, they are going to be approximated on different grids. The first one will be on a finer grid. The second one will be on a coarser grid. And I'm saying here, and I said it again, that it doesn't matter where the data is coming from. You can use real data, satellite observations, and so on, or you can use synthetic data, as long as you have the run of the PDE computed on a sufficiently large time scale. Why is that? Well, that's because you have to use this partition, and then you have to have a sufficiently large number of increments so that they are uncorrelated, and the larger the number of increments, the better the PCA procedure is going to be. Okay, so now I'm saying here that, of course, the calibration depends on the perturbation, the calibration depends on the parametrization, and it depends. So, you can have all sorts of types of noises: additive noise, multiplicative noise, transport noise. And the last type of noise is one that we have been working for a while, which is the stochastic advection by lead transport noise. Okay, so I am explaining here briefly again what you do for the additive noise, because that's the easiest one. And essentially what is done in here, you take this increment of the process that I've already explained. You divide by square root of delta t so that this is properly normalized. Then you end up with this sum in here where I have a 1 in here because of the 1 in here. And then this one is going to be normal with mean and some covariance matrix. And then for this one, the application of PCA is really straightforward. It's immediate when you can compute both n and the psi k in one go. These are the samples. They have to be decorrelated. So you have to choose the samples of the increments sufficiently far apart in time so that they are decorrelated, and then you have to apply the PCA to these samples. And the point here is that computing the psi k, these values, is really data dependent, right? So they depend on this data. That means what? That means that if you change this data, you can get different psi k. So there's no unique set of psi k that you end up with. If you change the data, you might get different psi k's. Okay, so there is no uniqueness in here. Indeed, a distribution can be approximated in many different ways via Gaussians. Okay, so let's go and look at this at the model, at the case study. So this is for the stochastic rotating shower water model, and possibly a lot of people in the audience know about this. So we have two variables. One is a horizontal velocity denoted here by u. So this is a vector, and you have here the sort of x and y velocity, and the other one is the height of the fluid column. So I'm putting the height in here, right? So there's an explanation here. How is the height? I'm not going to go into details about this, but this is just a pictorial description of what the height is. It's basically the distance between the bottom topography and the fluid surface. So I'm presenting here a bit more details about the implicit model. So again, this is the equation. This here is the material derivative. Then I have a term which is due to the rotation of the Earth. F is the Coriolis parameter, and is explicitly given here. It's a standard term included to model the effect of the rotation of the Earth. And then here is another term, which is the effect of gravitation. And this term in here, this is sort of pressure term, is g, the gravitational acceleration, multiplied by the gradient of h. H is the height of the column, and it satisfies this equation, the standard equation, the density equation that appears, the conservation equation that appears in here. Now, this is the standard implicit rotating shower water model, which can be written in a very short format like this. dxt is f of xt plus f of xt is equal to 0, and I write this. I want to hide all of these other terms in here in this way, because the next step will be to add stochasticity to this. So why this particular model? This particular model we chose because it is a simplification of the 3D primitive equations, which I'm sure people know are the equations that are the basis of the dynamical core for numerical weather prediction. And they, despite being simplification, they do retain key aspects of the dynamics for atmosphere and the oceans, including gravity waves. And they have a lot of very good mathematical and theoretical properties. For example, they are the critical part of a certain action function. In other words, the solution satisfies the Hamilton principle. The actual solution is distinct from others because it's a stationary value of this action function. So there's physics, there's a lot of physics involved in this. They also preserve circulation. This means what? This means that if we start with a closed curve and you follow and you integrate the velocity around this closed curve, and then you look what happens to the integral of the velocity along the curve as it is transported by the same velocity, this is constant. which is for any fluid, this is something that applies to. So this is that you know, the fact that we have this property for the rotating shallow water equation, it's a good property to have because it's a good model for a fluid to have this. Okay, next. So as I said, we want to incorporate stochasticity in this, but the way in which we incorporated stochasticity was not ad hoc. And this comes from the work of my collaborator from Imperial, Daryl Holm, which introduced this methodology to incorporate stochasticity through variational principles, right? In the sense that the stochastic version, the version that is stochastically parameterized, satisfies the same properties as the deterministic version. And the way this is done is to say that we're going to take the parcels of fluid that initially evolve according to the velocity and perturb them. So you perturb the parcels of fluid with perturbations coming from this type of stochastic terms. So xi's are the xi's that appear previously in the standard, in the generic form of the SPDs, and these are Brownian motions. And the reason for doing that is that they still are critical paths for a stochastically perturbed action function. They preserve circulation, and they are very good in modeling the effects of the aerosol scales, as you should see in a minute. And this new methodology is a standard methodology which you can apply to any geophysical fluid dynamics model. It's called stochastic advection by lead transport stochasticity. Okay, so now I'm going to show you. So this is the stochastic version, and it should perhaps come as a surprise that the stochastic version really is not something that you have seen before. So you don't end up with something which is additive. You don't end up with something which is multiplicative, but something which is much more complicated. And I'm just going to show you how the stochastic PDE looks like, and then you can hide it, and then it's just going to be, it's going to look like this, where we have the first part coming from the deterministic version and the second part coming from the stochastic version. Okay, so this now looks like the SPD that we had before, and the aim here is to try to compute this size in here that appear everywhere else. And if you ask, well, does this stochastic PD have a solution? The answer is yes, and we have a paper out which proves the well-posedness of this SPD. Okay, so let me show you some numerics. So for the numerics, we resolved the PDE on a fine grid that is like a rectangle, and it has size 2000 bit by 320. So it's long this way and short this way. And it's a finite difference scheme on a staggered Arakawa grid. I'm sure people know this is quite standard. And the actual physical model is a square, a rectangle, as I said, with this many kilometers in the X and Y direction. Essentially, what we wanted to do, we wanted to take a strip around the Earth in the atmosphere. So this is an application for the atmosphere. So for this, we had periodic boundary conditions in the east-west direction and slip-free boundary conditions in the north-south direction. We had a starting condition, but we ran it. We had a burn-in period to arrive to something that looks a bit more interesting. So we ran the SPD for the PDE for 1,000 time steps of this size, so that we have an initial condition of the model state. So this was the initial condition, and this was the surface elevations, that h, and this is the x velocity and the y velocity. Now, for this, we only used h as calibration data. So we restricted our observations just to h, and the reason for that is that this is essentially easy to compute, easy to estimate, and it's a lot harder to have as data velocity in both X and Y direction. So that was our calibration data. And here I'm explaining again for this particular model how the calibration is done. So I'm not going to go through the details. The only point that I need to make in here is that before you get to apply the PCA method, you have to solve a linear hyperbolic equation because of the complicated form of the parameterization. But once you have that, then you can apply the PCA. So there's an intermediate steps, and I'm not going to go through this because the mathematics is quite elaborate in that you have to apply to end up with the data that is inputted in the PCA methodology. Okay. And this explains how the how the low pass filter is introduced, and also how the correlation time is computed. But I'm not going to go through all of this. I'm just going to start showing you some results. Now there's 8 experiments that we've done, and they are divided into 3 categories. So first we discretized 4 times. We took every 4th point in X and Y direction. And so we coarsened the grid like that. And we computed everything based on this. We calibrated everything based on this. And then we took every 8th point in X and Y direction, and we did the calibration for this. We did 2 types of PCAs, one that explains the variance at 90% and one that explains the variance at 99%. And then when we did the simulation, so that we see the various realizations of the SPD, we had first 50 realizations and then 100 realizations in both cases. So that's why we have 8. We had 3 parameters. Therefore, we had 2 to the power 3, 8 numerical experiments. So I'm going to show you first what comes out of the calibration when in one particular case. So here we took the coarsest of the 2, where you take every 8th point, and then we took enough size to explain 99% of the variance. Now, what I'm showing in here, the size are 2-dimensional. So this is the first psi. But this is the psi that explains kind of the most of the variance, and then you go down, and then you get further psi that explains further variance, as it were. Now, what we found out that we had to have to explain 99% of the variance, you have to have 9 psis, which means you have to have 9 independent sources of noise. The first size was this one, so you see here a lot of the core scale coming up, and then as you go along down to the 9th one, you see a lot of the small scales influences in there. Okay, so for this particular discretization, for this particular parameterization, salt parameterization, when you take every 8th point, you're coarsening every 8th point, and you want to explain 99% of the variance, you need 9 different sources of noise. Not just 1, not just 2, but 9. Okay, so then what we did in here, we say, okay, we've done this, right? Now let us run the true. This is the truth. So you take the solution at 1 point, say 140 by 20, and the solution obviously has elevation and the 2 velocities. You take the actual solution, and this, the red one, is the solution on the fine grid projected on the coarse grid at this point, and you compare it with the realization of the SPD in there. And the point that we need to see in here is that they are not far apart. They are not far apart. The uncertainty is there. There's uncertainty, right? They begin to oscillate, right? But they are not far apart. Okay. And obviously, we start with some initial uncertainty, because not even the initial condition can be certain. But this initial uncertainty really continues, and in some sort, it envelops. It envelops the truth. And this is the right thing that we need to see. And this is for 100 particles. Okay, so I have a lot of things that I need to show you, but I'm aware that there's 10 minutes left. So I'm just gonna show you one, and then I'll just flash through the other ones. So this is for the ensemble spread. The ensemble spread is a measure of the uncertainty, right? So the bigger the ensemble spread, the bigger the uncertainty. So it's a quantification of the uncertainty. So what you see in here, let's just home into one of these things. So what you see in here, you see two sets in here, right? The ones from the bottom are the ones that correspond to the finer of the two coarse grids, right? So this means what? This means that there is little uncertainty here. I just choose every fourth point. There is uncertainty, the bias, there is a spread, but it's not as big as the one that corresponding to taking every eighth grid. So you have to, in order to model the subscript dynamics, subscript scale for the one that you take every eighth grid, you have to put a lot more noise than this one. And if you look, for example, at this one here, they are paired up. The one on the bottom are the one where you explain only 90% of the variance. But if you want to explain more, you have to have 99%, then you have to jump. So there's a jump in here, but it's not as essential, it's not as big as the one that occurs as a result of coarsening further the fine scale dynamics. And there's each one of them has two of these trajectories, and that is the difference is that one takes 50 particles, then one takes 100 particles. So you don't gain much by adding more particles. Even with 50 particles, you are there in terms of quantifying of the uncertainty. So that's what you have for the ensemble spread. Okay, let me go to the next page. All right, sorry. So this was the spread. The RMSE is the same. And the same with the L2 errors. We have similar results. In all of these three, the part that influences the additional stochasticity is the coarsening of the scale. Okay, so final remarks. We introduced a generic calibration method for stochastic geophysical fluid analysis models. The calibration is Eulerian in nature, in the sense that you actually have to have the solution at the points of the grid. There is an alternative one which is Lagrangian calibration, where you need to know data for the evolution of the fluid of parcels. So this is something that we've done before. The calibration method can be applied for any choice of noise, additive, multiplicative, transport noise. We chose the salt noise because there's a lot of theoretical justifications of this choice of noise. And the answer is that this type of parameterization really does generate a suitable ensemble spread to explain the subgrid scales. And then you can, once you have this parameterization, once you have this ensemble, then you can use it to do data assimilation. And in effect, we have also done data assimilations after we calibrate this, but this is not the subject of my talk. And we did test it with additive noise, and it did show that additive noise was wrong. There was too little spread, and really the solutions diverged very quickly. In other words, the SPDs and the PD projected on the grid, on the coarse grid, will diverge. Which indicated that really additive noise is not a physical noise. Okay, so as I promised, I'm just going to share this slide. If people are interested, just type Stuart, STUOD, and you'll end up with our website. This is an ERC Synergy project that is ongoing and is going to finish in 2026. So we are roughly halfway through the project. We want to do lots of things related to modeling for the upper ocean dynamic, uncertainty quantification, introduction of stochasticity, data assimilations, and so on. We are very excited about the forthcoming SWOT data, and we're preparing for that and working very hard to develop the data assimilation methodology for SWOT data. And people are interested, just send an email to either me or any of the other PIs. The PIs are Bertrand Chaperon from IFREMER, myself and Daryl Holm from Imperial College London, and Etienne Memin from INRIA. We have lots of activities, including monthly sandboxes, annual hackathon, annual Steward conferences, and we welcome postdocs and PhD students to come and visit us. Okay, and this is some papers that I've written, and I will stop here and thank you for your attention.
Yeah, thank you very much, Dan. Thanks a lot for the great presentation. So any questions?
Possibly I spoke too fast.
No, they'll be coming. I can ask a question. So you mentioned on the additive noise. I have a few, but I can start with this one. On the additive noise, like that things didn't work, and so do you add like additive noise in that particular case, like at every fine time step or over a large time step? And also, what's the shape of the additive noise?
Okay, so maybe I should share. Let me share the screen again.
Like you're still using PCA, right, to do that?
Yes. So let me go back. Let's see. So this is the stochastic version. So the point for that, so we have a specific form for this operator, right?
Yep.
And this is integrated in respect to the cylindrical Brownian motion. So we did there, we just took this out, right? So the end result was that we just added a sum.
Oh, okay. So without no shapes then, no shapes, right?
We shape. Sorry. So let me just go back to the beginning. So this Brownian motion here.
Got it.
So there's a shape that the space is space dependent, right? So it is still space dependent. You still say, well, I mean, I'm doing a good job because I want to add noise which is space dependent. It's a different value for each point of the grid. It's not the same value. We then apply the PCA to get this size. So you get the size for each point on your grid, and then you solve your SPDs. And despite doing that, the spread was small, and it was going. The SPD was diverging very fast.
All right. And so then there is no link. I mean, I guess it would be the same. You could also have the like a link between the Brownian motion amplitudes and the connections to try to have that depend on the state. But in some sense, that's what the calligraphic G of X, right, is doing.
Well, yes. So okay. So in this format, so this is coming from your PD, right? So this is, you can't do anything about it. This is given to you. Somebody comes and say, we're using the primitive equations. That's what you use. You course on that. So you can't play around with this. What you can play around is by choosing this operator in here. So it's going to be your choice to say, okay, I'm going to use one operator or another operator. I think this is the suitable operator to put in front of my noise, right? So this is your choice. And then you say you're going to integrate this with respect to this noise. So the calibration is a calibration of the noise, but of course it's going to depend on your choice of M, right? So you have to choose first M, and then you calibrate according to the choice of M. So of course you're going to get different size depending on what choice of M do you have. And the M that we chose was coming from this salt methodology, because it really had the right properties. to model fluids. But it is a very popular thing, not just in the applied community, but also in the theoretical community, to just simply have additive noise added to your PDE. It's very easy to analyze, and it gets very good results theoretically. But what you try to prove is that when you calibrate it properly, according to the data that comes from the fine scale model, you actually show that the size that come out will push the SPDs in directions in the wrong direction.
Oh, got it. Okay. Thank you. Any
You're
other questions? I guess everybody is in the audience is already in vacation, thinking
Okay.
about maybe food or family or friends or loved ones that you may see.
Good.
Any other questions? Maybe I'll ask another question on the computational cost. Like, do you have any suggestions or how to control that? In particular, like the different. I mean, I see the 512 and the 64, and then there's the additional cost, right, of solving the stochastic components. And then, comparing the ensemble at high resolution to coarse resolution. What do you foresee, right? Since we're talking about mathematics of planet Earth, so let's say ECMWF, let's say, using your approach.
Okay, so this is a very good question. Essentially, the reason why we want to do this calibration, we want to work on coarse scales, is because we feel that there is a lot of save. Working on fine scales is okay, but there's these subgrid scales dynamics that no matter how fine your scale is going to be, you're not going to get there anyway. But working the other way by coarsening, then you can have a lot of realizations. And having a lot of realizations is good. It's good for forecast, but it is also good for data assimilation. And the reason why it's good for data assimilation is because I'm doing particle filters. For particle filters, you do need a lot of these realizations, because then you apply procedures where you select the right realization, and then you perturb them, and so on and so forth. And this is really very important. It's very important that you get enough of these realizations. So by using, you save a lot of computational effort. You save a computational effort. So in the models that we looked at, we had every eighth point. That means that you had a save of 1/60, but it was much more than that, because you work with a much coarser grid. Then the time intervals could be coarser. So you save both because the space grid, but also because the time grid was coarser. So the save was really massive. Now, in terms of what ECMWF is doing, that's a different story, because they don't, they have a lot of computational effort at their disposal. But what I understand from them is that they still want to have probabilistic forecast. And for the probabilistic forecast, it's, in my opinion, to be better to use a coarser version of your dynamical core and produce a lot of this. But once you do that, then you have to parameterize the stochasticity. So I think that's I think that's where it's useful to have these properly parameterized coarse scale models.
Got it. Yeah. You also, in answering this question, you also shed some light onto the prior question, is that if you integrate the coarser grid on a larger time step, then obviously you definitely need to have a stochastic parameterization that depends on the state, right? So that basically is multiplicative. Yeah.
Exactly.
If you have a shorter time step, but then you don't gain that aspect, then it might be okay to have quite a bit or most of the noise as additive, in the sense as you integrate with time, it will project on state and then depend on, create new states because of that and amplify. But if you have a larger time step, that won't work. Yeah. Okay.
Yeah. So in fact, this corresponds to what we observed in our numerics, that for short-term forecast, you don't have time to see the difference in stochasticity.
Exactly. Yeah.
Right. So, but as soon there was a threshold by after which the two really diverge. Now it could be that you can say, all right, so I'm only gonna stay with short-term forecasts, and I'm gonna assimilate my assimilation step will be smaller than the short-term forecast, and that makes sense. That makes sense.
Yep.